Imagine something so bright it makes an entire galaxy look dim. Not a star, not an explosion. Something far stranger. At the center of certain galaxies, there is an object no wider than our solar system that pours out more light than 1,000,000,000,000 suns combined. It outshines hundreds of billions of stars at once, and the source of all that energy is not nuclear fusion, not matter burning, but matter falling. Falling towards something from which nothing ever returns. A supermassive black hole. That alone would be remarkable. But here is what makes it genuinely unsettling. Some of these objects exist so early in the universe's history, so massive and so luminous, that by everything we understand about how cosmic structures grow, they should not be there at all. Before we go any further, if you find this kind of deep exploration fascinating, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, let's begin. Think about a galaxy for a moment. Not as a photograph you have seen in a textbook or on a screen, but as what it actually is. A galaxy is a collection of stars, hundreds of billions of them in many cases. Each star is a nuclear furnace, a massive ball of hydrogen and helium undergoing fusion at temperatures of millions of degrees in its core. Each one is pouring energy into the universe. Our sun alone produces about 383 trillion watts of power every single second. That is an almost incomprehensible amount of energy from just one ordinary star. Now multiply that by 200 billion or 300 billion. That is what a large galaxy does. It shines with the combined light of hundreds of billions of suns spread across a structure that might span 100,000 light years from edge to edge. A galaxy is one of the most luminous things in the universe. It is a city of stars, vast and brilliant and powerful. And yet, there are objects that make an entire galaxy look faint by comparison. Objects so luminous that when astronomers first detected them in the late 1950s and early 1960s, they could not figure out what they were. These objects appeared as tiny points of light in the sky, almost like stars. They did not look like galaxies. Galaxies, even very distant ones, usually appear as fuzzy patches of light, because they are extended objects spread across space. But these things look sharp, concentrated, point-like. Their spectra were strange. The light coming from them did not match any known type of star. The wavelengths of their emission lines were shifted by enormous amounts toward the red end of the spectrum. This redshift did not make sense if the objects were nearby. But if you assume the redshift was caused by the expansion of the universe, which stretches light to longer wavelengths the farther it has traveled, then these objects had to be billions of light years away. And that created an immediate problem. If something is billions of light years distant and still appears as a visible point of light in our telescopes, it must be extraordinarily, almost absurdly bright. Nothing known to physics at the time could explain that much energy coming from what appeared to be a single point in the sky. These objects were initially called quasi-stellar radio sources because many of them were strong emitters of radio waves, and they looked like stars through a telescope. That name was eventually shortened to quasar. And once astronomers understood what they were looking at, the picture that emerged was one of the most astonishing in all of physics. A quasar is not a star. That is the first and most important thing to understand. Despite the name, despite the appearance, a quasar has nothing to do with stellar fusion. A quasar is the extremely luminous core of a distant galaxy. It is the center of a galaxy, not the galaxy itself, but its very heart, blazing with so much energy that it drowns out everything around it. When you look at a quasar through a telescope, you often cannot see the galaxy at all. The central point of light is so overpowering that the hundreds of billions of stars surrounding it are lost in the glare. It is like trying to see a firefly next to a searchlight. The firefly is there, but you cannot make it out because the searchlight is simply too bright. So what is happening at the center of that galaxy to produce this kind of luminosity? The answer is a supermassive black hole. Not just any black hole, a black hole with a mass of millions or even billions of times the mass of our Sun. Now, most large galaxies have supermassive black holes at their centers. Our own galaxy, the Milky Way, has one called Sagittarius A star, with a mass of about 4 million times the mass of the Sun. The Andromeda Galaxy has one that is roughly 100 million solar masses. These black holes sit at the gravitational centers of their galaxies, and in most cases, they are quiet. They are not actively consuming large amounts of matter. They are just sitting there, massive and invisible, exerting their gravitational pull on nearby stars and gas, but not producing significant radiation. But sometimes, a supermassive black hole is not quiet. Sometimes, it has a supply of matter falling toward it. Gas, dust, the shredded remains of stars that wandered too close. When that happens, the black hole becomes what astronomers call active. The region around it lights up. Energy pours out. And in the most extreme cases, when the supply of matter is large and the black hole is massive, the result is a quasar, the most luminous sustained sources of energy in the known universe. This is what astronomers mean by an active galactic nucleus. The nucleus of a galaxy is its center. When the supermassive black hole at that center is actively consuming matter and radiating enormous amounts of energy, the nucleus is described as active. There is a whole spectrum of active galactic nuclei, from relatively modest ones that produce only moderate amounts of extra radiation, to the most extreme ones, the quasars, which can outshine their entire host galaxy by factors of hundreds or even thousands. Now here is the critical insight that makes quasars so remarkable. The energy does not come from inside the black hole. Nothing comes out of a black hole. That is the whole point. Once something crosses the event horizon, the boundary surrounding the black hole from which not even light can escape, it is gone. No energy, no information, no matter can return from beyond that boundary. So if the energy is not coming from inside the black hole, where is it coming from? The answer is the accretion disk. When matter falls toward a supermassive black hole, it does not simply drop straight in like a rock falling into a well. If the matter has any sideways motion at all, which it almost always does because gas clouds and stars in a galaxy are always moving in various directions, it cannot fall directly to the center. Instead, it spirals. Conservation of angular momentum, one of the most fundamental laws of physics, forces the matter into a rotating disk around the black hole. Think of water draining out of a bathtub. The water does not fall straight down, it spirals, forming a vortex. The same principle applies here, except the scale is almost inconceivably larger. This disk of spiraling material is called an accretion disk, and it is where all the action happens. Imagine an enormous whirlpool of gas, dust, and plasma swirling around a central drain. The analogy is imperfect because a bathtub drain removes water to somewhere else, whereas a black hole removes matter from the observable universe entirely. But the visual picture is useful. As the material spirals inward, it gets compressed. Particles of gas that are closer to the black hole orbit faster than particles farther out, just as planets closer to the Sun orbit faster than planets farther away. This difference in orbital speed creates friction between adjacent layers of the disk, and friction generates heat. Enormous, extraordinary heat. The inner regions of an accretion disk around a supermassive black hole can reach temperatures of millions of degrees. The gas is so hot that it becomes plasma, a state of matter where electrons are stripped from atoms and everything exists as a soup of charged particles radiating energy furiously. This is where the energy comes from. Gravitational potential energy is being converted into kinetic energy and then into thermal energy through friction and compression as the material spirals ever closer to the event horizon. The gas gets hotter and hotter. It radiates more and more intensely, and by the time it reaches the innermost regions of the disk, just before it crosses the event horizon and is lost forever, it has released a staggering amount of energy. How much energy? This is where things become truly remarkable. The efficiency of gravitational accretion around a black hole is far greater than any other energy-generating process we know of. Nuclear fusion, the process that powers every star in the universe, converts less than 1% of the rest mass energy of its fuel into radiation. When hydrogen fuses into helium inside the Sun, about 0.7% of the mass of the hydrogen is converted to energy according to Einstein's famous equation E equals mc squared. That 0.7% is what makes stars shine, and it is enough to power a star for billions of years. But gravitational accretion around a black hole can convert somewhere between 5 and 40% of the rest mass energy of the infalling material into radiation. The exact percentage depends on the properties of the black hole, and we will explore why shortly. But even at the lower end, 5%, the numbers are extraordinary. If a black hole accretes a mass equivalent to our Sun, it can radiate energy equivalent to 5% of the Sun's total mass energy. That might not sound like much in percentage terms, but remember, E equals mc squared. The speed of light is an enormous number. The speed of light squared is a truly staggering number. Even a small percentage of the rest mass energy of an entire Sun's worth of material is a phenomenal amount of energy. And the upper end of that efficiency range is nearly 10 times higher. This makes gravitational accretion onto a black hole the single most efficient process for converting matter into energy that exists in the known universe. It is far more efficient than nuclear fusion, far more efficient than chemical reactions, far more efficient than any process humans have ever engineered or even conceived. The only thing more efficient would be matter-antimatter annihilation, which converts 100% of mass into energy, but that does not occur naturally on the scales we are discussing. Now, the amount of energy a quasar actually produces depends on two things: the mass of the black hole and the rate at which matter is falling onto it. A more massive black hole has a larger accretion disk, higher temperatures, and more gravitational energy to release. A higher accretion rate means more fuel is being consumed per unit of time, which means more energy per unit of time. The most luminous quasars are powered by black holes of billions of solar masses, accreting matter at rates close to their theoretical maximum. These quasars produce luminosities that are almost impossible to put into human terms. The most powerful quasars radiate at luminosities of around 10 to the 47 or 10 to the 48 ergs per second. In more familiar terms, that is roughly 10 trillion to 100 trillion times the luminosity of the Sun. A single quasar, a single point-like region at the heart of a galaxy, producing more light than 10 trillion suns. Our entire Milky Way galaxy, with all of its 200 to 400 billion stars, produces a total luminosity of roughly 10 to 30 billion times that of the Sun. That means the most powerful quasars are hundreds or even thousands of times more luminous than the entire Milky Way. One tiny region at the center of a galaxy, smaller than our solar system, outshining everything else in that galaxy combined by a factor of 1,000 or more. That is what a quasar is. That is the scale of energy we are dealing with. Let me ground this with a sense of physical size, because the scale disparity is part of what makes quasars so shocking. The Milky Way is roughly 100,000 light years across. That is the distance light travels in 100,000 years, moving at about 300,000 kilometers every single second. The galaxy is enormous. It would take you 100,000 years at the speed of light to cross it. And all of the galaxy's light, all of the energy produced by its hundreds of billions of stars, comes from a structure spanning that colossal distance. Now consider the accretion disk of a quasar. The size of an accretion disk depends on the mass of the black hole and the properties of the infalling material. But for a typical quasar powered by a black hole of 1 billion solar masses, the region producing most of the luminosity might be a few light days to a few light weeks across. A light day is the distance light travels in one day, about 26 billion kilometers. A few light weeks might be 100 billion kilometers or so. That sounds large, and it is large by human standards. but compared to a galaxy, it is tiny. The luminous core of a quasar is roughly a millionth of the diameter of its host galaxy. It would be like having a flashlight bulb that somehow produced more light than an entire continent covered in floodlights. The bulb is there, you can measure it, but the amount of light coming from that tiny speck defies all intuition. Astronomers actually confirmed the small size of quasar emission regions through an observation that at first seemed puzzling. Quasars vary in brightness. Their luminosity fluctuates over weeks and months. Some quasars can brighten or dim by a significant fraction over the course of just a few days. Now, there is a fundamental rule in physics that limits how quickly an object can change its overall brightness. An object cannot change its brightness coherently on a timescale shorter than the time it takes light to cross it. If a source of light is 1 light year across, the fastest it can vary in a coordinated way is on a timescale of about 1 year. If it varies in just a few days, it must be no larger than a few light days across. The rapid variability of quasars confirmed that the emission region must be extraordinarily compact. It is physically small, yet it radiates more energy than everything else in the galaxy put together. This realization struck the astronomy community with enormous force when it first became clear in the 1960s and 70s. The idea that a compact region could outshine an entire galaxy seemed almost impossible. At the time, no known physical process could explain it. Nuclear fusion could not produce that much energy in that small A space. Chemical reactions were completely inadequate. Gravitational accretion onto a supermassive black hole was the only mechanism that worked. It was the only process known to physics that could extract that much energy from that small A volume. And this realization led to another profound conclusion. If quasars are powered by supermassive black holes, and if quasars exist at the centers of galaxies, then supermassive black holes must be common features of galaxies. This turned out to be correct. Over the following decades, astronomers found evidence for supermassive black holes at the centers of nearly every large galaxy they examined. The Milky Way has one. Andromeda has one. The giant elliptical galaxy M87 has one with a mass of 6.5 billion solar masses. Nearly every large galaxy contains a supermassive black hole at its center. Most of them are dormant, not actively accreting large amounts of matter, so they are not producing quasar-level luminosities. But they are there, remnants of a more violent past. And at some point in their history, many of them probably were active. Many of them probably shone as quasars billions of years ago when there was more gas available for them to consume. The universe was denser in the past. Galaxies were closer together. Gas had not yet been used up by star formation or blown away by previous episodes of quasar activity. The conditions for feeding a supermassive black hole were far more favorable in the early universe than they are today. This means that quasars are not exotic, alien objects disconnected from normal galaxies. They are a phase that galaxies go through. A quasar is what happens when a normal galaxy's central black hole is being fed large amounts of gas. It is a temporary state, not a permanent one. When the gas supply runs out, or when the quasar's own ferocious energy output heats and expels the surrounding gas, the quasar turns off. The black hole goes quiet, and the galaxy returns to being an ordinary, non-active galaxy like the Milky Way is today. Our own galaxy's central black hole, Sagittarius A star, is currently a sleeping giant. It accretes only tiny amounts of matter and produces only a feeble trickle of radiation, compared to what it could produce if it had a proper supply of fuel. But billions of years ago, the Milky Way's central black hole may well have been active. It may have been a quasar, lighting up the young Milky Way like a cosmic lighthouse. Every quasar is a galaxy with a temporarily hyperactive center. And many ordinary-looking galaxies we see today were once quasars, billions of years ago, when conditions were different and more gas was available. The radiation from a quasar does not just come in the form of visible light. Accretion disks are so hot and so energetic that they produce radiation across the entire electromagnetic spectrum. The outer regions of the disk, where temperatures might be thousands or tens of thousands of degrees, produce infrared and visible light. The inner regions, closer to the black hole, where temperatures climb into the millions of degrees, produce ultraviolet radiation and X-rays. Some quasars also produce gamma rays, the most energetic form of light. And as I mentioned, many quasars emit strongly in radio wavelengths as well, which is actually how the first quasars were discovered. Radio telescopes in the 1950s and 60s picked up strong radio signals coming from what appeared to be point-like sources in the sky. It was only when optical telescopes looked at the same positions and measured the redshifts of the light that astronomers realized these sources were incredibly distant and therefore incredibly luminous. The fact that quasars radiate across the entire electromagnetic spectrum is actually an important piece of evidence that supports the accretion disk model. A single temperature source would radiate at a specific range of wavelengths, but an accretion disk has a range of temperatures. The outer parts are cooler and radiate at longer wavelengths. The inner parts are hotter and radiate at shorter wavelengths. The resulting spectrum is a combination of radiation from all these different temperature zones, which is exactly what we observe when we study the light from quasars in detail. There is another feature of many quasars that adds to their extraordinary nature. Many quasars are surrounded by clouds of gas at various distances from the central engine. These gas clouds are illuminated and energized by the intense radiation from the accretion disk. When the radiation hits these clouds, it heats them and causes them to emit light at specific wavelengths, producing what astronomers call emission lines in the quasar's spectrum. The widths and velocities of these emission lines tell us about the conditions in the gas clouds, how fast they are moving, how dense they are, how hot they are. Some of these clouds are moving at thousands of kilometers per second, flung outward by the radiation pressure from the quasar, or orbiting at tremendous speeds close to the black hole. Studying these emission lines has been one of the primary ways astronomers have learned about quasars. By analyzing the light, they can determine the mass of the central black hole, the rate at which matter is being accreted, the size of the emission region, and the conditions in the surrounding gas. It is remarkable how much information is encoded in light. A single beam of photons arriving at a telescope after a journey of billions of years carries within it a detailed record of the conditions at its source. The temperature, density, chemical composition, and velocity of the gas that emitted or absorbed it are all encoded in the precise pattern of wavelengths. You can learn the fundamental properties of an object billions of light years away, simply by carefully analyzing the photons that reach your telescope. This is how astronomers have built up such a detailed understanding of quasars, despite the fact that no human being will ever visit one. So this is what a quasar is, in physical terms. It is the hyperactive nucleus of a galaxy. It is powered by matter spiraling into a supermassive black hole through an accretion disk that converts gravitational energy into radiation with extraordinary efficiency. The accretion disk is small, often no larger than our solar system, but it can outshine hundreds of billions of stars. The quasar radiates across the entire electromagnetic spectrum, from radio waves to gamma rays. It can vary in brightness over days or weeks, confirming its compact size, and it is surrounded by clouds of gas that are heated and accelerated by the intense radiation. A quasar is not magic. It is not exotic physics. It is gravitational energy conversion, the most efficient energy process in the known universe, operating at scales that dwarf anything else. And the fact that we can see quasars from billions of light years away, the fact that their light has traveled for most of the age of the universe to reach our telescopes, tells us something profound about just how much energy they produce. They are cosmic beacons, visible across the entire observable universe. The most distant quasar ever detected lies at a redshift of about 7.6, meaning its light left when the universe was only about 700 million years old. That light has been traveling for over 13 billion years to reach us, and we can still see it. We can still detect the photons from an accretion disk that was shining when the universe was an infant. That is the power of a quasar. And this raises a question that has troubled astronomers for decades. If a quasar requires a supermassive black hole of hundreds of millions or even billions of solar masses to produce that kind of luminosity, how did such a massive black hole come to exist when the universe was only 700 million years old? How do you build something that enormous in such a short amount of time? The universe was barely getting started. The first generation of stars had only recently ignited. The first galaxies were still assembling from smaller fragments of gas and dark matter, still pulling themselves together under gravity. The cosmic web of structure that we see today was only just beginning to take shape. Everything was young, raw, and unfinished. And yet, there at the center of a young galaxy sits a black hole so massive and so well-fed that it outshines everything around it. A black hole that contains 1 billion times the mass of our sun or more, somehow already fully formed and furiously active when the universe itself was still in its infancy. That is the question at the heart of this story. That is what makes quasars not just spectacular, but deeply puzzling. The physics of how they work, the accretion disk, the gravitational energy conversion, the radiation, all of that is well understood. But the question of how the engine itself, the supermassive black hole, managed to grow so massive so quickly in the early universe, remains one of the most challenging open problems in modern astrophysics. And as we are going to discover, the answer is not simple. In fact, astronomers are still working on it. And some of the proposed solutions are almost as extraordinary as the quasars themselves. To truly understand how a quasar works, you have to understand the engine at its center. And that engine is a supermassive black hole. Now, most people have a vague sense of what a black hole is. They know it is something with gravity so strong that nothing can escape. They know it is dark. They know it is dangerous. But the details, the actual physics of what a supermassive black hole is, and how it interacts with the matter around it, are far stranger and more specific than the popular image suggests. And those details are essential for understanding why quasars are as powerful as they are. A supermassive black hole is defined by its mass. These objects range from about 1 million times the mass of the Sun at the lower end to tens of billions of times the mass of the Sun at the upper end. The Milky Way's black hole, Sagittarius A star, which we mentioned earlier at about 4 million solar masses, sits at the modest end of the supermassive category. It is a relatively small supermassive black hole. Moving up the scale, the black hole at the center of the galaxy NGC 1600 has a mass of about 17 billion solar masses. That is over 4,000 times more massive than the Milky Way's black hole. And there are black holes even larger than that. The black hole in the galaxy, known as TORN 618, has a mass estimated at roughly 66 billion times the mass of the Sun. That is a single object containing more mass than some entire small galaxies. If you could somehow weigh it, it would outweigh all the stars in many dwarf galaxies combined. These are among the most massive single objects in the universe. More mass than entire small galaxies compressed into a single gravitational entity that warps space-time so profoundly that nothing within its boundary can ever leave. But here is the strange thing about black holes. Despite containing all that mass, they are not physically large in the way you might expect. A black hole is defined by its event horizon, the invisible boundary in space beyond which nothing, not matter, not light, not any form of information, can escape. The size of the event horizon is determined by the black hole's mass through a quantity called the Schwarzschild radius, named after the German physicist Karl Schwarzschild, who calculated it in 1916, just months after Einstein published his general theory of relativity. The Schwarzschild radius is directly proportional to mass. Double the mass of a black hole, and you double the radius of its event horizon. For a black hole with the mass of our Sun, the Schwarzschild radius is about 3 kilometers. That means if you could somehow compress the entire mass of the Sun into a sphere just 6 kilometers across, it would become a black hole. For the Milky Way's central black hole, with a mass of 4 million solar masses, the Schwarzschild radius is about 12 million kilometers. That is roughly 17 times the radius of the Sun. So our galaxy's supermassive black hole has an event horizon that is relatively modest in size. You could fit it comfortably inside the orbit of Mercury. But for the truly massive black holes that power the most luminous quasars, the event horizon gets much larger. A black hole of 1 billion solar masses has a Schwarzschild radius of about 3 billion kilometers. That is roughly the distance from the Sun to Uranus. So the event horizon of such a black hole would be comparable in size to the orbit of Uranus in our solar system. A black hole of 10 billion solar masses would have an event horizon stretching about 200 times the distance from Earth to the Sun, extending roughly 5 times farther than the orbit of Pluto. These are enormous regions of space from which nothing can return, and yet, compared to a galaxy, they are still tiny. An event horizon the size of our solar system is immense by human standards, but it is vanishingly small compared to a galaxy that spans 100,000 light years. Everything inside the event horizon is hidden from the outside universe. We cannot see inside. We cannot receive any information from inside. We cannot send a probe in and get data back. The event horizon is not a physical surface like the surface of a planet. There is no wall you could touch, no material boundary you could detect with instruments. It is a mathematical boundary defined by the curvature of space-time itself, a point of no return written into the geometry of the universe. If you were falling into a supermassive black hole, you would not feel anything special as you crossed the event horizon. There is no wall, no barrier, no flash of light, no alarm bell. Space-time is smooth at the horizon of a large black hole. You would simply pass from a region of space where escape is still theoretically possible to a region where it is not. You might not even realize you had crossed it, but once across, your future is determined. You will be pulled inexorably toward the singularity at the center, a point of theoretically infinite density where the known laws of physics break down and our equations give nonsensical answers. For a supermassive black hole, the journey from the event horizon to the singularity could take hours or even days of your own experience time, depending on the mass. But the outcome is the same regardless. Nothing returns. Now, none of this interior physics matters directly for understanding quasars because all the energy production happens outside the event horizon. But understanding the event horizon matters because it defines the inner edge of the accretion disk. The closer matter can get to the event horizon before falling in, the more gravitational energy it can release. And this is where things get interesting because the inner boundary of the accretion disk is not exactly at the event horizon. It is at something called the innermost stable circular orbit, often abbreviated ISCO. The innermost stable circular orbit is the closest distance at which matter can orbit a black hole in a stable circular path without spiraling inward uncontrollably. Outside the ISCO, matter in the accretion disk can orbit in roughly circular paths, slowly losing energy through friction and gradually spiraling inward. But inside the ISCO, no stable orbit exists. Matter that crosses this boundary falls rapidly toward the event horizon, plunging inward with very little time to radiate additional energy. So the ISCO effectively determines how much energy the accretion disk can extract from the infalling matter. The closer the ISCO is to the event horizon, the deeper the gravitational well the matter falls through before it plunges in, and the more energy it releases. For a non-spinning black hole, the ISCO is located at 3 times the Schwarzschild radius. This means matter can orbit stably down to 3 times the radius of the event horizon, and no closer. For a maximally spinning black hole, however, the situation is dramatically different. A spinning black hole drags space-time around with it through an effect called frame dragging. This warping of space-time allows the ISCO to shrink much closer to the event horizon. For a black hole spinning at its maximum rate, the ISCO can be right at the event horizon itself. This means matter in the accretion disk can spiral much closer to the black hole before it plunges in. It falls through a deeper gravitational well and releases much more energy. This is why the spin of a black hole matters so much for quasar luminosity. A rapidly spinning black hole can be dramatically more efficient at converting matter into energy than a non-spinning one. The difference is huge. A non-spinning black hole converts about 5 to 6% of the rest mass energy of the accreted matter into radiation. A maximally spinning black hole can convert up to about 42%. That is an enormous difference, nearly an order of magnitude, and it comes entirely from how close the accretion disk can get to the event horizon. But the accretion disk is not just a simple smooth flow of gas spiraling inward. The physics of how angular momentum is transported within the disk, which is necessary for matter to actually move inward rather than just orbit forever, is one of the most important problems in astrophysics. And for decades, it was one of the most puzzling. Here is the issue. For matter to spiral inward through the disk, it must lose angular momentum. Angular momentum is a conserved quantity. A parcel of gas orbiting at a certain radius has a specific angular momentum, and it will stay at that radius unless something removes some of that angular momentum. In a simple, smooth gas disk, ordinary molecular viscosity, the kind of friction you experience when you stir honey, is far too weak to transport angular momentum at the rates needed to explain the observed luminosities of quasars and other accreting systems. The disk would just sit there, barely evolving, producing almost no energy. The solution came in 1991 when the physicists Stephen Balbus and John Hawley demonstrated that even a weak magnetic field threading through an accretion disk creates a powerful instability called the magnetorotational instability. This instability generates turbulence within the disk, and that turbulence acts like an effective viscosity that is billions of times stronger than ordinary molecular viscosity. The turbulence efficiently transports angular momentum outward through the disk. As angular momentum is carried outward, the matter that loses it spirals inward. The faster angular momentum is transported, the faster matter falls toward the black hole, and the more energy is released. This discovery was a breakthrough. It explained how accretion disks could work. It explained why they could transport matter inward at the rates needed to power quasars. And it connected the physics of quasars to the behavior of magnetic fields and plasma in a fundamental way. The accretion disk is not a calm, orderly flow. It is turbulent, chaotic, threaded with magnetic fields that are constantly being stretched, twisted, and amplified by the differential rotation of the disk. This magnetic turbulence is what drives the entire engine. Without it, matter could not efficiently lose angular momentum. The disk could not feed the black hole at sufficient rates, and quasars as we know them would not exist. And magnetic fields do something else that is equally spectacular. They are responsible for one of the most dramatic features of many quasars: relativistic jets. Not all quasars produce jets, but many do. And the jets that some quasars produce are among the most extraordinary structures in the entire universe. A relativistic jet is a narrow beam of plasma, ionized gas, launched from the immediate vicinity of the black hole at speeds approaching the speed of light. These jets emerge from the polar regions of the accretion system, perpendicular to the plane of the accretion disk, and they shoot outward in opposite directions like twin searchlights piercing through the galaxy and beyond. They can extend for thousands of light years. Some extend for hundreds of thousands of light years, reaching far beyond the boundaries of their host galaxy and plowing into the intergalactic medium, the thin gas that fills the space between galaxies. Where the jets slam into this intergalactic gas, they create enormous lobes of hot, radio-emitting plasma that can span millions of light years from end to end. These radio lobes were some of the first features associated with quasars to be detected, because they are powerful sources of radio emission visible with radio telescopes. The jets carry enormous amounts of energy. They heat and push aside gas over vast distances. They inflate enormous bubbles in the surrounding medium that can be detected in radio wavelengths and X-rays, sculpting the environment around the galaxy on scales far larger than the galaxy itself. The exact mechanism that launches these jets is still an area of active research and debate. But the leading models involve the interaction of magnetic fields with the spinning black hole or with the inner regions of the accretion disk. In one scenario, magnetic field lines that are anchored in the accretion disk get twisted and wound up by the disk's rotation. This creates a magnetic structure that collimates and accelerates plasma along the rotation axis, flinging it outward at relativistic speeds. In another scenario, the magnetic field threads the event horizon of the spinning black hole itself. And energy is extracted directly from the black hole's spin through a process proposed by the physicist Roger Blandford and Roman Znayak in 1977. In this picture, the rotational energy of the spinning black hole is converted into the kinetic energy of the jet. The black hole literally powers the jet by slowing down its own rotation. This is one of the most remarkable ideas in astrophysics. A black hole, an object from which nothing can escape, powering an outflow of energy that travels at nearly the speed of light. The energy does not come from inside the event horizon. It comes from the rotational energy of the space-time around the black hole, the ergosphere, a region outside the event horizon where space-time is dragged so forcefully by the black hole's spin that nothing can remain stationary. Energy can be extracted from this region, and the Blandford-Znayak mechanism is the leading theoretical framework for how jets tap into it. The material in these jets moves at extraordinary speeds. In some cases, the plasma has been measured traveling at more than 99% of the speed of light. At such speeds, relativistic effects become important. One fascinating consequence is something called superluminal motion. When a jet is pointed almost directly toward us, a combination of the jet's high speed and the geometry of the situation creates an optical illusion where the material appears to move faster than the speed of light across the sky. It is not actually exceeding the speed of light. That is impossible. But the apparent velocity as seen from Earth can appear to be several times the speed of light due to the way light travel times compress when the source is moving nearly straight at you. When astronomers first observed this apparent faster-than-light motion in quasar jets in the 1970s, it caused considerable confusion until the relativistic explanation was understood. Quasars with jets pointed almost directly at Earth receive a special name. They are called blazars. Because of the geometry, with the jet aimed at us, the radiation from the jet is enormously boosted by relativistic beaming. The jet's emission is concentrated in the forward direction and amplified. As a result, blazars are among the most violently variable objects in the sky. They can change in brightness by large factors over hours or days as conditions in the jet fluctuate. They are some of the brightest gamma-ray sources in the sky because the ultra-high energy radiation from the jet is beamed directly toward our telescopes. Now, the luminosity of a quasar is governed by two key quantities: the mass of the black hole and the accretion rate, the amount of matter falling onto the disk per unit of time. A more massive black hole means a larger gravitational field, a larger accretion disk, higher temperatures, and more total energy output. A higher accretion rate means more fuel is being processed, so more energy is released per second. But there is a natural limit to how fast a black hole can accrete matter, and this limit is one of the most important concepts in quasar physics. This limit is called the Eddington luminosity, named after the British astrophysicist Arthur Eddington. The concept is elegantly simple. As matter falls toward a black hole and the accretion disk radiates energy, that radiation pushes outward. Photons carry a momentum, and when they interact with the infalling gas, they exert a force, radiation pressure. The more luminous the disk, the stronger this outward radiation pressure. At some point, if the luminosity gets high enough, the outward radiation pressure exactly balances the inward pull of gravity. This is the Eddington luminosity. It is a critical threshold. Beyond this point, Any additional infalling matter would be blown away by the radiation before it could reach the disk. The radiation literally prevents more fuel from arriving. It is a self-regulating mechanism. If the black hole tries to accrete too fast, the resulting radiation blows the fuel away. If it accretes more slowly, the radiation is weaker and more fuel can fall in. The Eddington luminosity depends only on the mass of the black hole. A more massive black hole has a stronger gravitational pull, so it can hold on to infalling matter against stronger radiation pressure. This means it can accrete at a higher rate and produce a higher luminosity before hitting the Eddington limit. For a black hole of 1 billion solar masses, the Eddington luminosity is roughly 30 trillion times the luminosity of the Sun. That is an extraordinary amount of energy, but it is a ceiling, not a choice. The black hole cannot easily exceed this luminosity through normal accretion. This limit has profound consequences for how fast a black hole can grow. If a black hole is accreting at the Eddington rate, the maximum rate allowed by this balance between radiation pressure and gravity, it adds mass at a specific pace. Not all the accreted matter ends up as black hole mass, of course. Some of it is converted into energy and radiated away, but the rest adds to the black hole, increasing its mass and therefore increasing its Eddington luminosity, allowing it to accrete even faster. The result is exponential growth. The black hole doubles its mass in a characteristic time called the Salpeter time, named after the astronomer Edwin Salpeter, and it is roughly 45 million years, assuming a standard radiative efficiency of about 10%. That means a black hole accreting at the Eddington limit continuously will double its mass approximately every 45 million years. Starting from a seed of, say, 100 solar masses, which is the kind of black hole that could form from the death of a massive star in the early universe, you would need to double the mass roughly 23 times to reach 1 billion solar masses. 23 doublings at 45 million years per doubling gives you a bit over 1 billion years of continuous, uninterrupted, maximally efficient accretion. That sounds like it should work. The universe at the time we see the earliest quasars was about 700 million to 1 billion years old. So you would need almost every single one of those years to be spent accreting at the maximum possible rate, with no interruptions, no pauses, no episodes where the gas supply ran out, and no time lost to the initial formation of the seed black hole itself. And that is assuming the accretion efficiency is relatively low, around 10%, so that most of the accreted mass actually adds to the black hole rather than being radiated away. At higher efficiencies, more energy is radiated per unit of mass accreted, which actually means less mass is added to the black hole per unit of fuel consumed. A more efficient engine grows slower in mass for the same amount of fuel. The math gets tight, very tight, in many cases impossibly tight, which is the core of the problem we will explore further. But before we get to that problem, there is one more aspect of quasar physics that is crucial for understanding how these objects fit into the larger story of the universe. Quasars do not just passively shine, they actively shape the galaxies they live in. The enormous energy output of a quasar, both in the form of radiation and in the form of jets and outflows, interacts with the gas in the host galaxy in profound ways. This process is called active galactic nucleus feedback, or simply AGN feedback, and it is one of the most important concepts in modern galaxy formation theory. Here is why it matters. When astronomers build computer simulations of how galaxies form, starting from the initial conditions of the early universe and letting gravity pull matter together over billions of years, the simulations produce galaxies that are too massive. Without some additional process to stop gas from cooling and forming stars, the simulated galaxies accumulate far too many stars. They become much brighter and more massive than the real galaxies we observe in the universe. Something must be preventing all that gas from turning into stars. Something must be heating the gas, pushing it out of the galaxy, or keeping it from collapsing. That something, astronomers now believe, is the energy output from the central supermassive black hole. When a quasar is active, its radiation heats the surrounding gas to millions of degrees. Gas at those temperatures cannot collapse to form stars. It is too hot. The pressure is too high. The gas is effectively sterilized, kept in a state where star formation is shut down. Additionally, the jets and outflows from the quasar can physically drive gas out of the galaxy entirely. Observations have shown quasar-driven outflows moving at speeds of thousands of kilometers per second, carrying masses equivalent to hundreds of solar masses per year out of the host galaxy. These outflows can strip a galaxy of its fuel for star formation, effectively quenching the galaxy and turning it from a blue, star-forming system into a red, dead, elliptical galaxy. This feedback process creates a deep and fundamental connection between the mass of the central black hole and the properties of the galaxy around it. And indeed, astronomers have discovered a remarkably tight relationship between the mass of a galaxy's central black hole and the mass of the galaxy's central bulge, the dense concentration of stars in the inner regions. This relationship, called the M-sigma relation, because it connects black hole mass to the velocity dispersion of stars in the bulge, which is a measure of how fast those stars are moving and therefore how much mass the bulge contains, holds across a wide range of galaxy sizes. Small galaxies with small bulges have relatively small central black holes. Giant galaxies with massive bulges have enormous central black holes. The correlation is remarkably tight, spanning several orders of magnitude in both black hole mass and bulge mass, which suggests that the black hole and the galaxy have grown together over cosmic time, regulating each other's development through feedback. The galaxy feeds the black hole, and the black hole's energy output regulates the galaxy's growth. They are locked in a feedback loop that shapes both of them over cosmic time. This is why quasars matter far beyond their own spectacular luminosity. They are not just bright curiosities. They are architects of the galaxies they inhabit. The energy output from a quasar episode can determine whether a galaxy continues forming stars or stops. It can determine whether a galaxy remains a blue spiral or transforms into a red elliptical. It can affect the distribution of gas not just within the galaxy, but in the surrounding intergalactic medium. Jets from powerful quasars have been observed heating gas in galaxy clusters, preventing that gas from cooling and forming new galaxies. The influence of quasars extends far beyond their own host galaxies. So a quasar is more than just a bright point of light at the center of a distant galaxy. It is a supermassive black hole actively feeding through an accretion disk, converting gravitational energy into radiation with extraordinary efficiency, potentially launching relativistic jets that extend far beyond the galaxy's borders and pouring out so much energy that it reshapes the galaxy and its surroundings. The physics is gravitational, magnetic, and relativistic all at once, operating simultaneously across wildly different scales. The scales are vast, from the innermost stable orbit just outside the event horizon to jets that stretch hundreds of thousands of light years into intergalactic space. And the consequences ripple through the entire history of galaxy formation and evolution. All of this is well established. The accretion disk model, the role of magnetic fields, the Eddington limit, the reality of jets, the importance of AGN feedback. All of these are supported by decades of observation and theory. Quasars are among the best understood extreme objects in astrophysics. We know how they work. We know why they shine. We know how they affect their environments. The physics is clear. What is not clear, what remains one of the great open puzzles of modern astrophysics, is how the central engines of the earliest quasars, the supermassive black holes powering them, managed to grow so massive so quickly in the first billion years of cosmic history. The Eddington limit sets a speed limit on growth. The age of the universe sets a deadline. And for the most distant, most massive quasars we have found, those two constraints do not easily fit together. The engine works beautifully. The mystery is how the engine was built so fast. Now we arrive at the part of the story where everything gets uncomfortable. Because astronomers have found quasars that, according to the straightforward physics we just laid out, should not be there. Not because the physics is wrong. The physics works beautifully. The accretion disk model is solid. The Eddington limit is well understood. The relationship between black hole mass and luminosity is clear. The problem is not with the physics of how quasars shine. The problem is with the timeline. Some quasars exist so early in the history of the universe, powered by black holes so impossibly massive, that there simply does not appear to have been enough time for them to form. And this is not a minor tension. It is one of the most serious open problems in modern astrophysics. To understand why this is such a problem, you first need to understand the timeline of the universe itself. The universe began with the Big Bang approximately 13.8 billion years ago. In the first few 100,000 years after the Big Bang, the universe was a hot, dense soup of particles and radiation. There were no stars, there were no galaxies, there were no black holes. There was just hydrogen, helium, a trace of lithium, and an enormous amount of light, all packed together in a rapidly expanding, cooling plasma. About 380,000 years after the Big Bang, the universe cooled enough for atoms to form. Electrons combined with protons to make neutral hydrogen atoms. Before this moment, the universe was opaque. Light was trapped, bouncing endlessly between charged particles. But once atoms formed, the universe suddenly became transparent. Light could finally travel freely through space. That light is still traveling today. We detect it as the cosmic microwave background, a faint glow of radiation that fills every direction of the sky. After this, the universe entered a period astronomers call the cosmic dark ages. There were no sources of visible light. No stars had formed yet. The universe was filled with dark gas, mostly hydrogen and helium, slowly being pulled together by gravity into denser and denser clumps. If you could somehow have been there, you would have seen nothing. Complete darkness in every direction. Just cold gas, slowly, silently gathering under the pull of gravity. Dark matter was also clumping together during this period, forming halos that would eventually host the first galaxies. The Dark Ages lasted for roughly 100 to 200 million years. Then, sometime around 100 to 250 million years after the Big Bang, the first stars ignited. These were the population 3 stars, the very first generation of stars the universe ever produced. They formed from pure hydrogen and helium because no heavier elements existed yet. Heavier elements like carbon, oxygen, iron, and all the other elements that make up planets and people did not exist at this point. They had not been created. They would only be forged later, inside these first stars and in the supernova explosions that ended their lives. The first stars were likely very different from the stars we see today. Without heavy elements to help gas cool efficiently, the clouds that formed these first stars could not fragment into small clumps the way modern star-forming clouds do. In modern star-forming regions, heavy elements help the gas radiate away its heat, allowing it to compress into relatively small clumps that become stars similar in mass to the Sun or smaller. But in the pristine primordial gas of the early universe, there were no such coolants. The gas could only cool through much less efficient processes involving hydrogen molecules. As a result, the gas remained hotter and the clumps that formed were much larger. Many theoretical models suggest the first stars were massive, perhaps tens to hundreds of times the mass of the Sun. Some models propose that a fraction of them could have been truly enormous, several hundred solar masses or even more. These massive first stars lived fast and died young. A star of 100 solar masses burns through its nuclear fuel in just a few million years. When such a star dies, if it is massive enough, its core collapses to form a black hole. A star of 100 solar masses might leave behind a black hole of perhaps 20 to 50 solar masses, maybe more depending on how much mass is lost during the star's life and during the explosion. Stars at the upper end, those with initial masses of perhaps 200 to 300 solar masses, might collapse directly into black holes without a traditional supernova explosion at all. In certain mass ranges, roughly 130 to 250 solar masses, the star undergoes a process called pair instability, where radiation inside the core creates pairs of electrons and positrons, reducing pressure and triggering an explosion so powerful it destroys the star entirely, leaving no remnant at all. But above roughly 250 solar masses, the collapse is so overwhelming that even this process cannot unbind the star. It falls directly into a black hole containing a significant fraction of its original mass, possibly several hundred solar masses or more. So the first black holes in the universe were probably formed from the deaths of these massive first stars, somewhere around 150 to 300 million years after the Big Bang. These are called stellar mass seed black holes. And here is the critical question. Can one of these seed black holes, starting at perhaps 100 solar masses, grow into a supermassive black hole of 1 billion solar masses in the time available? Let us do the math carefully, because this is where the problem becomes concrete. We established that the Eddington limit sets a maximum rate at which a black hole can accrete matter through a standard radiative accretion disk. At this maximum rate, the black hole doubles its mass in roughly 45 million years. This is called the E-folding time, or the salpeter time. Each doubling multiplies the mass by 2. Starting from 100 solar masses, how many doublings do you need to reach 1 billion solar masses? 1 billion divided by 100 is 10 million. You need to multiply your starting mass by 10 million. Since each doubling multiplies by 2, you need to find how many times you multiply 2 by itself to get 10 million. 2 to the power of 23 is about 8.4 million. 2 to the power of 24 is about 16.8 million. So you need roughly 23 to 24 doublings to get from 100 solar masses to 1 billion solar masses. At 45 million years per doubling, that is about 1 billion to 1 billion and 80 million years. That is the minimum time required to grow a 100 solar mass seed into a billion solar mass black hole through continuous, uninterrupted, Eddington limited accretion. Now compare that to the age of the universe when we observe the earliest quasars. The most distant quasars known have been found at redshifts of 7 and above. A redshift of 7 corresponds to a time when the universe was only about 770 million years old. The most distant quasar confirmed as of recent observations, designated J0313-1806, lies at a redshift of about 7.64, corresponding to a time when the universe was approximately 670 million years old. And this quasar is powered by a black hole estimated at roughly 1.6 billion solar masses. Let that settle in for a moment. The universe was 670 million years old. The first stars probably did not form until 150 to 250 million years after the Big Bang. That means the first stellar mass black holes probably did not form until roughly 200 to 300 million years after the Big Bang. So from the formation of the first seed black holes to the time we observed this quasar, only about 370 to 470 million years have elapsed. That is far less than the 1 billion years of continuous Eddington limited accretion needed to grow 100 solar mass seed to 1 billion solar masses. The timeline does not fit, not even close. And the problem is actually worse than this calculation suggests, because the calculation assumes perfect conditions. It assumes the black hole accreted at the Eddington rate continuously, without any interruptions, for hundreds of millions of years straight. This is an extraordinarily optimistic assumption. In reality, accretion is not a steady, smooth process. The gas supply to the black hole depends on the environment. Gas has to be available in the vicinity of the black hole. It has to lose enough energy and angular momentum to actually fall inward. In the early universe, the first galaxies were still assembling. They were small, chaotic, undergoing mergers with other proto-galaxies. The gas supply would have been intermittent and uneven. There would have been periods where plenty of gas was available and periods where the black hole had very little to eat. Additionally, the black hole's own energy output works against it. As the accretion disk radiates, it heats the surrounding gas. If the gas gets too hot, it cannot fall inward efficiently. The radiation can blow gas away from the black hole, temporarily cutting off the fuel supply. This is the AGN feedback we discussed earlier. The very process that makes the quasar bright also limits how much matter the black hole can consume. It is a cruel paradox. The brighter the quasar shines, the more effectively it pushes away the very gas it needs to keep shining. A black hole accreting at the Eddington rate is right at the edge of blowing away its own fuel supply. Any fluctuation, any increase in luminosity beyond the Eddington limit, and the radiation pressure overpowers gravity and pushes the gas away. The black hole then has to wait for the gas to cool and settle back down before it can resume accreting. These interruptions cost time. And in the early universe, time was the one thing these black holes did not have. Every million years spent waiting for gas to return was a million years not spent growing. Astronomers have a term for this. It is called the duty cycle, the fraction of available time that a black hole actually spends accreting at or near the Eddington rate. A duty cycle of 100% would mean the black hole accretes continuously without pause. A duty cycle of 10% would mean it spends only 1/10 of the available time actively accreting, and the rest sitting idle, waiting for conditions to become favorable again. Observations of active galactic nuclei in the nearby universe suggest that typical duty cycles are somewhere between 10 and 30%. If that was also true in the early universe, it would multiply the required growth time by a factor of 3 to 10. Instead of needing 1 billion years of continuous accretion, you would need 3 to 10 billion years of elapsed time to accumulate the same mass. And the early universe did not have 3 billion years. It barely had 1. The duty cycle problem is another nail in the coffin of simple Eddington-limited growth from small seeds. There is another subtlety that makes the growth problem even more challenging. The efficiency of the accretion process itself works against rapid mass growth. Remember, the accretion disk converts a fraction of the rest mass energy of the infalling matter into radiation. This is what makes the quasar luminous, but every unit of energy that gets radiated away is mass that does not get added to the black hole. Einstein's equation tells us that energy and mass are equivalent. When the accretion disk radiates energy, it is effectively losing mass. The higher the radiative efficiency, the more energy is radiated, and the less mass is actually added to the black hole per unit of accreted material. A non-spinning black hole with a radiative efficiency of about 6% adds about 94% of the accreted mass to itself. But a rapidly spinning black hole with an efficiency of 30 or 40% adds only 60 to 70% of the accreted mass. The more efficient the engine, the slower the black hole actually grows in mass. This is deeply counterintuitive. A more efficient accretion disk produces more light, making a more luminous quasar, but it also means the black hole itself grows more slowly, because more of the fuel is being converted to radiation instead of being swallowed. So spinning black holes, which produce the most luminous quasars, actually grow slower than non-spinning ones. This is one of the deep ironies of quasar physics. The very property that makes a quasar spectacular to observe, its extreme luminosity, is a symptom of high radiative efficiency, which actually slows the growth of the black hole powering it. If the earliest supermassive black holes were spinning rapidly, which is plausible given that the infalling material in the accretion disk carries angular momentum that is transferred to the black hole over time, their growth would have been even slower than the standard Eddington calculation assumes. The timeline gets even tighter. You would need even more time to reach 1 billion solar masses, time that the young universe simply did not have. And the discoveries keep pushing the problem further. Over the past 2 decades, astronomers have found more and more quasars at earlier and earlier cosmic times. Each new discovery at a higher redshift is another challenge to the growth models. In 2001, the discovery of a quasar at redshift 6.4, powered by a black hole of roughly 3 billion solar masses, when the universe was only about 870 million years old, was already considered a serious puzzle. By 2011, a quasar at redshift 7.1 was found with a black hole of about 2 billion solar masses, when the universe was 770 million years old. Each successive discovery narrowed the available window of time for growth. Then came the James Webb Space Telescope. JWST, launched in December of 2021, is the most powerful infrared space telescope ever built. Its primary mirror is 6.5 meters across, giving it extraordinary light-gathering power. It can see further back in time and with greater sensitivity than any previous telescope, detecting the faint infrared glow of objects that existed in the first few 100 million years of cosmic history. Objects so distant that the expansion of the universe has stretched their light from visible and ultraviolet wavelengths all the way into the infrared, where only a telescope like JWST can detect them. And almost immediately after it began scientific operations, it started finding things that made the growth problem even worse. JWST has detected active galactic nuclei and growing black holes at redshifts of 8, 9, 10, and beyond. These are times when the universe was only 300 to 600 million years old. Some of these black holes appear to have masses of millions, or even tens of millions of solar masses, which might sound modest compared to the billion solar mass monsters powering the most luminous quasars. But at such early times, even a 10 million solar mass black hole is extremely difficult to explain through standard Eddington limited growth from a stellar mass seed. One particularly striking JWST discovery was a system called UHZ1, identified in 2023. This appears to be a growing black hole at a redshift of about 10.3, corresponding to a time when the universe was only about 470 million years old. The estimated black hole mass is in the range of 10 million to 100 million solar masses. For a black hole to have reached 10 million solar masses by the time the universe was less than 500 million years old, starting from a stellar mass seed of a few tens or hundreds of solar masses, is extraordinarily challenging with Eddington limited accretion. The time is simply not there. Another striking case is GNZ11, one of the most distant galaxies ever observed. At a redshift of about 10.6, corresponding to a time when the universe was only about 430 million years old, JWST detected spectral signatures strongly suggesting the presence of an actively accreting black hole at its center. The nitrogen emission features observed in GNZ11's spectrum are characteristic of gas being energized by the intense radiation near an active galactic nucleus. If confirmed, this means a supermassive black hole was already in place and actively feeding when the universe had existed for barely 400 million years, pushing the timeline problem to an even more extreme degree. JWST has also revealed something else that complicates the picture further. It has found that supermassive black holes in the early universe appear to be overmassive relative to their host galaxies. In the local universe, in galaxies relatively close to us, there is a well-established relationship between the mass of a galaxy's central black hole and the mass of the galaxy itself. The black hole typically contains about 0.1 to 0.5% of the galaxy's total stellar mass. This relationship is tight and consistent across a wide range of galaxy types and sizes. But in the early universe, JWST observations suggest that some black holes are much more massive relative to their host galaxies than this local relationship would predict. The black holes seem to have grown faster than the galaxies around them, or they started bigger than expected, or both. In some cases, the black hole mass represents several percent of the total stellar mass of the galaxy, 10 to 100 times higher than the local ratio. This is another piece of evidence that something unusual was happening in the early universe, something that allowed black holes to accumulate mass more rapidly than standard models predict. Perhaps most surprising of all, JWST has uncovered an entire population of compact, reddish sources at high redshifts that astronomers have informally nicknamed little red dots. These objects appear to be dust-obscured active galactic nuclei, compact galaxies whose central black holes are actively accreting but are partially hidden behind veils of dust that redden their light. Before JWST, these objects were essentially invisible. They were too faint and too red for previous telescopes to detect. But JWST's infrared sensitivity has revealed them in large numbers, far more than anyone predicted. The sheer abundance of these little red dots suggests that actively growing black holes in the early universe were not rare exceptions or unusual outliers. They were common. The early universe may have been teeming with accreting supermassive black holes, most of them hidden from our view until JWST pulled back the curtain. This makes the growth problem not just about a handful of spectacular quasars, but about a widespread phenomenon that demands a widespread explanation. Let me be very clear about what is well established and what remains an open question, because this distinction matters. What is well established is that quasars exist. They are real. They have been observed in enormous numbers across a wide range of cosmic times. What is well established is that quasars are powered by accretion onto supermassive black holes. The accretion disk model is supported by decades of observational evidence, including the spectral properties of quasars, their variability, their polarization, and direct imaging of the immediate environment around supermassive black holes by the Event Horizon Telescope. What is well established is that the Eddington limit exists. It is a straightforward consequence of the balance between radiation pressure and gravity, and it has been confirmed in many astrophysical contexts. What is well established is that quasars with black holes of hundreds of millions to billions of solar masses existed when the universe was less than 1 billion years old. These detections are based on well-calibrated distance measurements using redshift, and the black hole masses are estimated using established methods based on the widths of spectral emission lines and the overall luminosity. What remains an open question is how these massive black holes formed so quickly. The standard picture of stellar mass seed black holes growing through Eddington limited accretion does not comfortably explain the most extreme early quasars. The math does not work without invoking special conditions, unusually massive seeds, periods of super-Eddington accretion, or rapid growth through mergers. This is the genuine scientific tension that the title of this episode refers to. These quasars should not exist in the sense that our simplest, most straightforward models of black hole growth cannot easily produce them in the time available. That does not mean the quasars are impossible. They clearly exist. The universe does not care about our models. It does what it does. What it means is that our understanding of how the first supermassive black holes formed is incomplete. Something is missing from the standard story. Either the seeds were bigger than we assumed, or the growth was faster than we assumed, or some combination of both. And figuring out which possibility is correct, or whether the answer is something else entirely, is one of the most active areas of research in astrophysics today. The tension is sharpened further by a simple observation about the distribution of early quasars. It is not just one or two anomalous objects that could be dismissed as statistical flukes or measurement errors. Surveys have now found dozens of quasars at redshifts above 6, many powered by black holes exceeding 1 billion solar masses. Whatever process created these early supermassive black holes, it was not a rare one-off event. It happened repeatedly across the early universe. It happened in many different galaxies in many different environments. Any successful explanation must account not just for the existence of one impossibly massive early black hole, but for a whole population of them scattered across the sky. The problem is systematic, not anecdotal. It requires a systematic answer. This is what makes the problem so compelling. It is not a speculative puzzle about exotic physics. It is a concrete, observational challenge. We can see these objects, we can measure their properties, we can calculate the time available for their growth, and the numbers do not add up unless we revise our assumptions about how the first black holes were born, or how quickly they grew. Consider the challenge from yet another angle. The very first stars, the population 3 stars that formed from pristine primordial gas, probably did not appear until about 150 to 250 million years after the Big Bang. These stars had to form, live their brief lives of perhaps 2 to 3 million years, and then die to create the first stellar mass black holes. So, the first black hole seeds probably did not appear until roughly 150 to 300 million years after the Big Bang. Now, the most distant quasars we see existed at about 670 to 800 million years after the Big Bang. That gives a window of roughly 370 to 650 million years for growth. Even at the generous end, 650 million years divided by 45 million years per doubling gives about 14 doublings. Starting from 100 solar masses, 14 doublings gives you about 1.6 million solar masses. That is a respectable supermassive black hole, but it is a factor of 1,000 short of 1 billion solar masses. You need another 10 doublings, another 450 million years, that simply are not available. Some researchers have pointed out that if the seed was more massive, say 10,000 solar masses instead of 100, the problem becomes somewhat less severe. From 10,000 solar masses, you need only about 17 doublings to reach 1 billion solar masses, which takes about 765 million years. That is closer to the available time, but still very tight. And it still requires continuous Eddington rate accretion with no interruptions for the entire duration. And it requires a seed of 10,000 solar masses, which cannot be produced by ordinary stellar death. No single star, no matter how massive, leaves behind a 10,000 solar mass black hole through normal stellar evolution and collapse. Creating a seed that massive requires a different formation pathway entirely. Something unusual had to happen in the early universe to produce such heavy seeds, and understanding what that something was is at the heart of the problem. There is also the question of environment. For a black hole to accrete at or near the Eddington rate, it needs a continuous supply of dense gas funneled into its vicinity. In the early universe, the first galaxies were small, perhaps only a few million to a few hundred million solar masses in total. The gas within them was being heated by the first stars, by supernova explosions, and by ultraviolet radiation that flooded the universe during reionization, when the first stars and galaxies ionized the neutral hydrogen that filled intergalactic space. All of these heating sources work against accretion. Hot gas has more pressure and is harder to compress. It resists falling inward. So even if a massive seed black hole existed, maintaining a continuous, uninterrupted supply of cool, dense gas to feed it for hundreds of millions of years is itself a significant challenge. The environment of the early universe was violent, dynamic, and hostile to the steady conditions that Eddington limited growth requires. All of these factors combine to create a problem that is robust and well-defined. It is not a matter of one uncertain measurement or one questionable assumption. The challenge comes from multiple independent lines of evidence. The quasars are there. Their redshifts are measured. Their black hole masses are estimated. The age of the universe at those redshifts is known. The Eddington growth rate is understood. And when you put all these pieces together, the standard picture struggles. Something beyond ordinary stellar mass seeds and ordinary Eddington limited growth is required to explain what we observe. This is science at its most exciting. Not because we have the answer, but precisely because we do not. The observations are pushing our theoretical understanding to its limits. The universe is showing us something we did not expect, and now we have to figure out what it means. The quasars that should not exist are not a failure of our understanding. They are an invitation to deepen it. They are telling us that the early universe was more complex, more dynamic, and more capable of producing extreme objects than our simplest models predicted. And the race to explain them is one of the most active and fascinating frontiers in astrophysics today. So, if the standard picture cannot explain how billion solar mass black holes appeared so early in cosmic history, what can? Astronomers have not given up. They have proposed several possible solutions, each with its own strengths and its own problems. None of them is fully confirmed. None of them has been definitively proven to be the answer. But each represents a serious, physically grounded attempt to resolve the tension between what we observe and what our simplest models predict. And together they paint a picture of an early universe that was far more dynamic, far more extreme, and far more creative in its ability to produce massive objects than anyone expected. The first proposed solution involves starting with a bigger seed. If the problem is that a stellar mass black hole of 100 solar masses cannot grow to 1 billion solar masses fast enough, then perhaps the first black holes were not stellar mass objects at all. Perhaps some of them were born much heavier, giving them a significant head start. This idea is called the direct collapse black hole model, and it is one of the most actively studied proposals in the field. The concept is straightforward in principle, though the conditions required are very specific. In the early universe, within the first few 100 million years after the Big Bang, there were regions where massive clouds of primordial gas, containing perhaps 100,000 to 1 million solar masses, were collapsing under their own gravity. Normally, as a gas cloud collapses, it heats up. That heat causes the gas to radiate energy, which allows it to cool and compress further. As it compresses and cools, it fragments into smaller and smaller clumps, each of which eventually becomes a star. This is the standard process of star formation that operates throughout the universe today. It produces populations of stars with a range of masses, from tiny red dwarfs to massive blue giants. But what if that fragmentation could be prevented? What if a collapsing gas cloud could be kept hot enough that it never fragmented into stars at all? If the gas remains hot and does not fragment, the entire cloud can collapse as one coherent mass. Instead of forming thousands of individual stars, it forms a single, supermassive object. And if that object is massive enough and lacks the internal processes to halt the collapse, it can fall directly into a black hole. Not a stellar mass black hole of a few tens of solar masses. A black hole of 10,000 to 100,000 solar masses. A direct collapse black hole. A seed that is already hundreds or thousands of times more massive than anything that ordinary stellar evolution could produce. The key question is, what could prevent the gas from fragmenting? The answer that theorists have proposed is ultraviolet radiation. Specifically, a strong background of ultraviolet light in the Lyman-Werner band. A specific range of ultraviolet wavelengths that is very effective at destroying molecular hydrogen. Molecular hydrogen is the primary coolant in primordial gas. Without molecular hydrogen, the gas cannot cool efficiently. If the molecular hydrogen in a collapsing gas cloud is destroyed by an external source of ultraviolet radiation, perhaps from a nearby galaxy or a cluster of young stars, the gas stays hot. It cannot fragment, and it collapses as a single enormous mass. Computer simulations have shown that under the right conditions, this process can work. A massive gas cloud bathed in sufficiently strong Lyman-Werner radiation can collapse without fragmenting, forming a supermassive protostar that grows rapidly by accreting gas from its surroundings. This protostar can reach tens of thousands of solar masses or more before it eventually collapses into a black hole. The result is a direct collapse black hole, a seed that starts at 10,000 to 100,000 solar masses, already far ahead in the race to become a billion solar mass monster. From such a massive seed, the growth problem becomes much more manageable. Starting at 100,000 solar masses instead of 100 solar masses removes about 10 doublings from the required growth. That saves roughly 450 million years. Now, the black hole only needs about 13 to 14 doublings to reach 1 billion solar masses, which takes about 585 to 630 million years at the Eddington rate. That fits more comfortably within the available time, especially if the seed formed early and the accretion was reasonably continuous. But the direct collapse model has challenges of its own. The conditions required are very specific, almost surgically precise. You need a massive gas cloud that is collapsing in the right way, with the right amount of angular momentum, exposed to the right intensity of Lyman-Werner radiation. Too little radiation and the molecular hydrogen survives. The gas cools efficiently and fragments into a cluster of ordinary stars instead of collapsing as one mass. Too much radiation and the gas might be heated so strongly that the thermal pressure prevents collapse entirely, and the cloud simply disperses. The Goldilocks zone of radiation intensity is narrow. The cloud must receive enough ultraviolet light to destroy its molecular hydrogen, but not so much that it gets blown apart. And the cloud must be pristine, composed of pure primordial hydrogen and helium, with essentially no heavy elements. Even a tiny trace of carbon or oxygen, amounts as small as 1/10,000th of the solar abundance, which are far more efficient coolants than molecular hydrogen, would allow the gas to cool and fragment, ruining the entire process. This means direct collapse black holes can only form from gas that has never been enriched by stellar processes, gas that has never been touched by the debris of previous generations of stars. In the early universe, such pristine gas existed, but it was already beginning to be contaminated by the first supernovae scattering metals into the surrounding environment. How common were these conditions in the early universe? That is an open question. Some theoretical calculations suggest they were rare, occurring in perhaps 1 in every 10,000 or 100,000 collapsing halos. Others suggest they might have been somewhat more common, depending on the exact spatial distribution of the first star-forming galaxies and the intensity of the radiation fields they produced. JWST observations of candidates like UHZ1, the growing black hole at redshift 10.3, may be evidence that direct collapse did occur. The estimated mass of that black hole, in the range of 10 million to 100 million solar masses at such an early time, is consistent with a direct collapse origin. But confirmation requires more data, more observations, and more theoretical work. The second proposed solution attacks the problem from a different angle. Instead of starting with a bigger seed, it proposes that the growth rate was faster than the Eddington limit normally allows. This is called super-Eddington accretion, and it challenges one of the fundamental assumptions we discussed earlier. The Eddington limit assumes that the accretion flow is roughly spherical, and that the radiation produced by the accretion must push against all the infalling material. But what if the geometry is different? What if the accretion flow is not spherical, but highly non-spherical, channeling matter inward along some directions, while allowing radiation to escape along others? In such a configuration, infalling gas could continue to pour in through an equatorial flow, or along narrow streams, while the radiation escapes through gaps or funnels along the poles. The radiation does not impede the inflow, because the radiation and the matter are moving in different directions. They pass by each other rather than colliding head-on. If this geometry is achieved, the effective accretion rate can exceed the Eddington limit by factors of several, perhaps even factors of 10 or 100 in extreme cases. This idea has theoretical support. Simulations of accretion flows in specific conditions, particularly when the gas supply is dense and arrives rapidly, show that super-Eddington accretion can occur. The accretion disk becomes geometrically thick, puffing up under the intense radiation pressure, and develops a structure where radiation escapes preferentially along the rotation axis, while matter continues to flow in through the equatorial plane. In these simulations, black holes can grow significantly faster than the Eddington limit would normally allow. If super-Eddington accretion occurred in the early universe, even for limited periods, it could dramatically accelerate black hole growth. A black hole accreting at 10 times the Eddington rate would double its mass in roughly 4.5 million years, instead of 45 million years. Even brief episodes of super-Eddington accretion, interspersed with longer periods of normal or sub-Eddington accretion, could provide the extra growth needed to explain the most massive early black holes. But super-Eddington accretion has its own challenges. It requires an extremely dense, sustained supply of gas. The gas must be delivered to the black hole's immediate vicinity at rates far exceeding what normal galactic processes typically provide. In the early universe, this might be possible during galaxy mergers, when enormous amounts of gas are funneled toward the center of the merging system, or in the dense environments of the first massive dark matter halos, where cool, primordial gas could stream inward along cosmic filaments and accumulate rapidly. But sustaining these extreme accretion rates for long periods is difficult. The very process of super-Eddington accretion produces enormous energy output that can heat and disrupt the gas supply. There is a self-limiting aspect to the process, similar to the feedback problem at the Eddington rate, but even more severe at higher accretion rates. There is also an observational challenge. If super-Eddington accretion was common in the early universe, we should see signatures of it. The radiation from a super-Eddington accretion disk would have different spectral properties than radiation from a standard Eddington limited disk. Identifying these signatures in the light from distant quasars is an active area of research, and some candidates for super-Eddington accretion have been proposed. But the evidence is not yet conclusive. The third proposed solution involves not growing a single seed at all, but assembling a massive black hole from the merger of many smaller ones. In the early universe, the first dark matter halos were dense, and the first galaxies were small and packed close together. As these proto-galaxies merged, which they did frequently in the dense early universe, the black holes at their centers would have been brought together. When two black holes get close enough, they lose energy through gravitational wave emission. These gravitational waves are ripples in the fabric of space-time itself, predicted by Einstein's general theory of relativity over a century ago, and first detected directly in 2015 by the LIGO Observatory in the United States. That first detection was one of the most important scientific achievements of the 21st century, confirming a prediction that had remained untested for 100 years. As gravitational waves carry energy away from the orbiting black holes, the black holes spiral closer and closer together until they merge into a single, more massive black hole in a cataclysmic event that briefly radiates more power in gravitational waves than all the stars in the observable universe radiate in light. If this process happened repeatedly in the early universe, with proto-galaxies merging frequently and their central black holes coalescing each time, you could build up a massive black hole relatively quickly without requiring sustained Eddington rate accretion. Each merger roughly doubles the mass. If a 100 solar mass black hole merges with another 100 solar mass black hole, you get a 200 solar mass black hole. If that one merges with another 200 solar mass black hole, you get 400, and so on. If mergers were frequent enough, this could provide significant mass growth, in addition to whatever accretion was happening between mergers. But there are problems with this scenario too. The main issue is getting the black holes to actually merge. When two galaxies merge, their central black holes are initially separated by large distances. They gradually sink toward the center of the merged galaxy through a process called dynamical friction, where the black holes lose energy through gravitational interactions with surrounding stars and gas. But this process can stall. When the two black holes get within a few parsecs of each other, roughly 3 to 10 light years, dynamical friction becomes less effective. The black holes can get stuck in a binary orbit, circling each other without getting close enough for gravitational wave emission to take over and drive them together. This is called the final parsec problem, and it has been a persistent challenge in theoretical astrophysics. Without some mechanism to bridge this gap, some way to extract the last bit of orbital energy and bring the black holes close enough for gravitational waves to take over, the mergers stall and the growth stops. In the early universe, the abundant gas present in our young galaxies might help solve this problem. Gas can exert drag on the orbiting black holes, extracting energy and driving them together faster than stellar dynamical friction alone. Dense, gaseous environments might bridge the final parsec relatively efficiently. But this remains an area of active simulation and debate. And even if mergers were efficient, they come with another challenge. When two black holes merge, the gravitational waves they emit carry not just energy but also momentum. This momentum is not always symmetric. If the two merging black holes have different masses or different spins, the gravitational waves can carry a net momentum in a specific direction, giving the merged black hole a gravitational recoil kick. This kick can be enormous, in some cases exceeding 1,000 kilometers per second. That is faster than the escape velocity of most early galaxies, which were small and had relatively shallow gravitational wells. If the merged black hole is kicked out of the galaxy, it is lost. It drifts off into intergalactic space, taking all that accumulated mass with it, and the galaxy has to start over with a new, smaller seed. Gravitational recoil kicks do not happen in every merger, and the magnitude depends on the specific properties of the merging black holes. But in the small galaxies of the early universe, even modest kicks could eject the merged black hole. This limits the effectiveness of the merger pathway for building truly massive black holes. There is also a fourth possibility that has gained attention in recent years. In the extremely dense nuclear star clusters that may have formed at the centers of the earliest protogalaxies, massive stars were packed so closely together that they could physically collide and merge with one another before they had time to exhaust their fuel and die. In these runaway stellar collision scenarios, one star grows by swallowing others, building up to thousands or even tens of thousands of solar masses in just a few million years. When this hypermassive star finally collapses, it produces a black hole far more massive than any single stellar death could create, potentially rivaling the direct collapse pathway in the mass of the seed it produces. The key requirement is an environment dense enough for these collisions to happen frequently, and the cores of early protogalaxies may have provided exactly those conditions. The honest answer, the scientifically accurate answer, is that we do not yet know which of these mechanisms is primarily responsible for creating the first supermassive black holes. It might be one of them. It might be all of them working together in different combinations, in different environments. Some early black holes might have formed through direct collapse and then grown through Eddington limited accretion. Others might have started as stellar mass seeds and experienced brief episodes of super-Eddington accretion that accelerated their growth. Still others might have assembled through a combination of accretion and mergers. The early universe was a diverse place, and different pathways might have operated simultaneously. What we can say is that the question is being actively investigated with the best tools humanity has ever built. JWST is providing unprecedented observations of the early universe, revealing black holes and quasars at times, and in configurations that challenge and constrain theoretical models. Gravitational wave detectors, both current ground-based observatories like LIGO and Virgo and future space-based missions like the planned LISA observatory, which is designed specifically to detect the low-frequency gravitational waves produced by merging supermassive black holes, will be able to detect mergers of massive black holes in the early universe, directly testing the merger pathway. If LISA detects frequent mergers of massive black holes at high redshifts, it would strongly support the merger scenario. If such mergers are rare, it would point toward direct collapse or super-Eddington accretion as the primary growth mechanisms. And there is already a tantalizing hint. In 2023, the Nanograv collaboration, which uses an array of precisely timed pulsars spread across the galaxy as a gravitational wave detector, announced evidence of a low-frequency gravitational wave background permeating the universe. This background hum is consistent with what you would expect from a vast population of supermassive black hole binaries, slowly spiraling toward merger across cosmic history. If confirmed, it would mean that mergers of supermassive black holes are not just theoretical possibilities, but ongoing events shaping the gravitational landscape of the universe right now. Increasingly sophisticated computer simulations running on some of the most powerful supercomputers in the world are modeling the conditions under which direct collapse and super-Eddington accretion can occur, tracking the flow of gas from cosmological scales down to the immediate vicinity of the black hole. The next decade of astrophysics will likely bring major progress on this question, possibly even a definitive answer. But let us step back from the details of seed masses and accretion rates and merger dynamics, and consider what quasars as a whole tell us about the universe. Because quasars are not just puzzles to be solved, they are among the most powerful tools astronomers have for understanding how the universe evolved. Quasars are extraordinarily bright, so bright that they can be seen across the entire observable universe. This makes them cosmic beacons, lighthouses that illuminate the universe at all epochs. When astronomers observe a distant quasar, the light from that quasar passes through billions of light years of intergalactic space on its way to our telescopes. That light interacts with gas along the way. Hydrogen gas between galaxies absorbs the quasar's light at specific wavelengths, leaving a pattern of absorption features in the quasar's spectrum. By analyzing these absorption features, astronomers can map the distribution of hydrogen gas throughout the universe at different cosmic times. This technique has been used to study the large-scale structure of the universe, to measure the density of intergalactic gas, and to understand how the universe transitioned from a neutral state, filled with neutral hydrogen gas, to an ionized state, where that hydrogen was stripped of its electrons by ultraviolet radiation from the first stars and quasars. This transition, called the Epoch of Reionization, was one of the most important transformative events in cosmic history. Before reionization, the universe was opaque to ultraviolet light. Neutral hydrogen gas scattered and absorbed ultraviolet photons, preventing them from traveling far. After reionization, the universe was transparent. Ultraviolet light could travel freely across billions of light years. The universe went from being foggy to being clear, and that transition changed everything about how structure could grow, how galaxies could interact with their environments, and how light could propagate through the cosmos. Quasars played a significant role in driving reionization itself. Their intense ultraviolet radiation ionized enormous volumes of surrounding gas, carving out vast bubbles of ionized hydrogen in the otherwise neutral intergalactic medium. Over time, these bubbles grew and eventually overlapped, filling the universe with ionized gas. The most distant quasars we observe, those at redshifts of 6 and 7 and beyond, sit right at the edge of the reionization epoch. Their spectra show clear signs that the surrounding universe was still partially neutral when their light was emitted. These quasars are not just objects of study. They are participants in the transformation of the universe from its dark, neutral infancy to the transparent, ionized state we see today. Quasars also trace the growth of structure in the universe. The most luminous quasars tend to live in the most massive galaxies, which themselves tend to live in the densest regions of the cosmic web. By mapping the locations of quasars across cosmic time, astronomers can trace how the large-scale structure of the universe evolved. Where the quasars are, the densest environments are. Where the densest environments are, the most massive dark matter halos are. And the distribution of those halos tells us about the fundamental parameters of cosmology, the density of matter, the nature of dark energy, and the initial conditions set by the Big Bang. There is also a remarkable cosmic narrative in the history of quasar activity across the universe's lifetime. Quasars were not equally common at all times in cosmic history. When astronomers survey quasars across a wide range of cosmic distances, measuring how many exist at each redshift, they find a striking pattern. Quasar activity peaked when the universe was about 2 to 3 billion years old, at redshifts of roughly 2 to 3. This era is sometimes called cosmic noon, the peak era of both star formation and black hole growth in the universe. During cosmic noon, galaxies were forming stars at the highest rates in cosmic history, converting enormous reservoirs of cold gas into new suns at rates 10 or 20 times higher than today's galaxies manage. And their central black holes were being fed at the highest rates as well, shining as quasars across the electromagnetic spectrum. The universe was awash in activity. Stars were being born and dying in enormous numbers. Galaxies were colliding and merging far more frequently than they do today, because the universe was smaller and galaxies were packed more closely together. Gas was flowing along cosmic filaments into the densest regions, feeding both star formation and black hole growth. Supermassive black holes were growing rapidly, shining as quasars and pouring energy into their surroundings. It was the most productive, most energetic, most creative epoch in the universe's history. After cosmic noon, quasar activity declined. The supply of cold gas needed to fuel both star formation and black hole accretion gradually diminished. Galaxies used up their gas. Quasar feedback blew gas out of galaxies and heated the intergalactic medium, making it harder for gas to cool and fall back in. Mergers became less frequent as the universe expanded and galaxies spread farther apart. The most massive black holes had already done most of their growing. By the present day, the universe is a much quieter place. Most supermassive black holes are dormant. Star formation rates are a fraction of what they were at cosmic noon. The epoch of the great quasars is largely over. We live in the universe's twilight years, cosmically speaking, long after the peak of activity. And this brings us full circle. A quasar is the most extreme manifestation of one of the most fundamental processes in the universe, the conversion of gravitational energy into radiation as matter spirals toward a point of no return. It is not magic. It is not mysterious in the sense that we do not understand the physics. We understand the physics beautifully. An accretion disk, heated by friction to millions of degrees, converting the gravitational potential energy of infalling matter into light with an efficiency that dwarfs nuclear fusion. A supermassive black hole at the center, defining the depth of the gravitational well, setting the scale for how much energy can be extracted. Jets of relativistic plasma launched along magnetic field lines, carrying energy across hundreds of thousands of light years. Radiation so intense, it can outshine hundreds of billions of stars, visible across the entire observable universe, shaping the evolution of galaxies and the intergalactic medium alike. All of this is well understood. The mechanism is clear. The observations confirm it. The theory explains it. But there, at the edge of our understanding, sits the question that will not go away. How did the engines get so big so fast? How did the universe produce billion solar mass black holes in less than 1 billion years? How did the most powerful beacons in the cosmos light up so early in cosmic history, when the universe was still assembling its first structures, still forming its first stars, still transitioning from darkness to light? We have ideas. Direct collapse black holes that skip the stellar stage entirely. Super-Eddington accretion flows that broke through the usual growth limits. Rapid mergers in the dense, chaotic environments of the young universe. Runaway stellar collisions in the first dense star clusters. All of these are plausible. All of them are being tested. But none has been proven. The answer may involve all of them, working together in ways we have not yet fully modeled. Or it may involve something we have not yet thought of. Some process unique to the conditions of the early universe that we have yet to discover. That is what makes quasars so compelling. They are not just spectacles. They are not just records in a catalogue of astronomical curiosities. They are signposts pointing towards something deep about how the universe works. They tell us that the cosmos is capable of producing extreme objects on timescales that strain our understanding. They tell us that the first billion years of cosmic history were more eventful, more violent, and more productive than our simplest models assumed. And they remind us that the universe is under no obligation to make sense to us on the first try. It does what it does. Our job is to keep watching, keep measuring, keep asking questions, and keep revising our understanding until the picture comes into focus. So the next time you look up at the night sky and see those familiar points of light scattered across the darkness, remember that some of the light reaching your eyes tonight has traveled for billions of years. And remember that out there, at distances almost beyond comprehension, there are objects so luminous they outshine entire galaxies. Objects powered by matter falling toward black holes so massive they strain the limits of what our theories can explain. Objects that should not be there, but are. Quasars. The brightest beacons in the universe. Real, observed, measured, and still not fully explained. And that is exactly what makes them one of the most extraordinary things the universe has ever produced. Thank you for joining me on this journey. If you found this exploration valuable, a like or subscribe would mean a lot. It helps this channel continue making these deep explorations of the cosmos. Good night, and sleep well under the stars. The universe is vast, strange, and full of things that challenge what we think we know. And that is what makes it beautiful.